All right. Before we do this problem, I have a demo to show you. So let me kind of get ready for that here. And this is one you could do at home, in the dorms, whatever, or at a restaurant, that kind of thing. What you do is just fill a cup with water. It's a little tough. Sometimes I don't even get it when I do it. So you do need to practice this. And then what you need in the cup is an ice cube. And so I had to bring an ice cube because I couldn't find one at school. So I brought one from home. Let's get a couple. So you put the ice cube in your cup of water. And you need a string. And you say to your buddy, hey, guess what? I bet with this string, I can pick up that ice cube with one hand. Boom, pick it up. They're like, sure, I'll bet that, for sure. So what you do is you put it on the ice cube like that. Okay, can you kind of see that? Let me dim the lights a little bit. Maybe it'll be easier to see. Okay, hopefully that's so you can see and then you get salt. And it's ideal if you have a salt shaker. That's way easier than what I have. I'm just going to use a little spatula here. I'm going to get a little salt on this. And then I'm going to try to cover this. See that? Cover that. And then pick it up. Little colligative properties right there, changing the melting point. And then you just win like a free dinner at the DC or whatever you betted with your buddy. Okay? It does take a little practice, but if you get that kind of string, kind of a small string, it works the best. Small kind of cotton string just like this one. Boom. Yeah. Pretty cool, huh? Just change the melting point a little bit by adding solute. All right, let me move this over. Okay. Let's go back to this problem right here. This is typical QK problem. I have a YouTube Q and K. All right, Haber process, same reaction as you saw before. Here, notice these are initial concentrations, not equilibrium. If they're initial, I must use Q, not K. So let's write first the reaction. We've got, what is it, N2 plus 3H2 goes to 2 NH3, and then Q is products NH3 initial squared over N2 initial times H2 initial cubed. Now let's put in the numbers that they gave us in the problems. NH3 is 1.0 times 10 to the minus 3 squared. N2 is 1.0 times 10 to the minus 5. And H2 is 2.0 times 10 to the minus 3 straight from the problem. And that's cubed for the H2. Get a Q value equal to, let's see what I got, 1.2 times 10 to the 7. By the way, what's the units? No units for Q or K. All right, is Q greater or less than K? It's crazy greater. Is that right? Did you see that? It's 10 to the minus 2 versus Q is this number. Okay, if Q is larger than K, which way are we shifting, right or left? Yeah, we're shifting to the left. So the shift will be towards the left in order to ultimately reach equilibrium. Because if Q is too big, there's too many products if Q is too big, so it has to shift to the left towards the reactants to reestablish equilibrium. Okay. Any questions on that? All right, I want to go back to figure 14.3 right now. Okay, in this figure, first of all, what was K? You remember what we said about K, large or small? It's really small in every picture. Is that okay? It's really small. Okay, now let's think about Q. Q, in this part right here, what's the value of Q right there? It has to be 0. How'd you know that? Yeah, there's no products to start with. And if Q is products over reactants initially, then Q initially would be 0. So which way will this shift if Q is 0? To the right. Is that okay towards the product? So in the first case, Q is 0, it shifts to the right, and that forms more products. Does that make more sense? Or does that make sense? So that's why we're forming products. Is that cool? We're forming products because that's what Q told us we would do. Okay, here is Q. What is the value of Q in the second picture? In this case, yeah, Q reaches infinity. It's very large. Why? Because the reactants are 0. So if Q is very, very large or infinite, which way does it shift? Right or left? Left. There's too much products initially. So it has to shift to the left to form more reactants. Is that okay? And notice what happens. We formed more reactants. We went from 0 reactants and formed more. You see how Q works? It's almost intuitive. You can imagine if there's no reactants, you got to form reactants. It follows Le Chatelier's principle. Okay, those are the easiest ones. We don't have the exact value for K, so the last one's a little harder. I guess we could do it. What's K? What's Q for the third case? Yeah, it'd be 1 because everything's 1. Is that okay? Everything's 1. So which way will it shift? Or let's say first, is Q larger or smaller than K? Larger, because we already determined that Q is small. Remember that? We already determined K was small in the previous time we looked at this. So Q is larger, so which way should it shift? To the left, and that means we should have more or less products. Which we do. Does that make sense? It shifts to the left, we have less product, more reactants. So that's the math behind what we're seeing here. That's what we're just doing. Okay. Yeah.
Can you explain experiments with why it's infinity?
Why is this one infinity for Q is a question. Is because remember it's initial products over initial reactants. Initial products is 1. Initial reactants is 0. 1 divided by 0, that's infinity. Essentially, don't tell your math professor that, but really it is. So that leads us to an infinite value of Q. Okay. Cool. Let's see what we just kind of tackled so far. We know this, we know the relationships of K, we did shift. Really, the only thing left, I have to do a little introduction first, say a little bit, but we're going to go into what's called the equilibrium table, which is the last section in the chapter. Okay, let me say a little bit first before we do that. And this, unfortunately, is not in your book, but it's in the reader on page 53. Let me make a scale or kind of an axis here. This is 0, this is infinity. And on this, for any reaction, K will be some constant. So you'll have K is a value. A value. Okay? K is a number for a reaction. Okay? And that's where equilibrium would lie. Now Q, though, is not a value. Let's get Q out here. Q can be anything from 0 to infinity. So can be anything. Okay? It can be any value depending on the initial conditions. But Q always wants to become K. So if Q happens to equal K, we're at equilibrium. If Q is greater than K, we shift which way? Again. Left, towards K. If Q is less than K, which would be over here, we have to shift to the right towards K. So it's always going towards K, but initially it could be different than K. Q can be any value between 0 and infinity, including those, and K is just a number It's not going to be 0 though. Okay, it could be close to 0 because it'd be a really, really small number, but it wouldn't include 0. Okay, so now I should discuss the difference between, you've heard the words favored and you've heard the word shift. Favored has to do with K and shift has to do with Q. And you don't want to confuse those two terms. Okay, here's what favored means. Make sure you get this down. Favored means, again, it has to do with K, and it indicates the size of K with respect to the number 1. So favored indicates the size of K with respect to the number 1. So if K is greater than 1, products are favored. If K is less than 1, reactants are favored. So you always compare to 1. Okay, shift is totally different. Shift is for Q, and shift compares Q to K. Okay, compares Q to K. So whether Q is bigger or larger than K, it tells you which way the shift is. So something could be favored and shift. It could be, it doesn't matter. Products could be favored, there could be a shift. Products could be favored, there could be no shift. All kinds of combinations of these two words are possible. So I just want to clarify, we've heard these two terms, make sure you know they're very different. One has to do with K with respect to 1, the other has to do with Q with respect to K. Okay. Let's move on. Section 7. Calculations. Yes, some of you are like, please, where are the numbers here? Calculations. I'm going to make a table that's about the size of what's left over here. And this is page 54 in the reader, and in the text. Whoa, where the heck are we in the text? We are somewhere. Okay, where did that go? We're on page 630 on the text. Okay, let me write down a reaction here. Again, our favorite general reaction. Just to do this in general at first, we'll do it specifically later. There's our reaction. Now I'm going to make a little table, as you'll see. And you'll see something like this also in the reader. And then something kind of like this in the textbook, sort of, in words though. Okay. Let's say I'm going to make now an I row. And I stands for initial concentration. And it could be pressure too, but we're going to work with concentrations at this moment. Okay? And let's say those are the variables. For A, the initial concentration is I. For capital B, the initial concentration is J. Capital C, it's K. And let's just say for capital D, that compound, it's L. Okay? I, J, K, and L. All right, now let's go to the next row in our table. This is going to be called the C row. And C row has to do with change. Stands for C for change. Okay? And there's two possibilities, and change has to do with Q. Okay, change has to do with Q. So there's two possibilities. Q can be greater than K, and the second possibility, Q can be less than K. Okay, so we're going to have both of those. If Q, again, if Q is greater than K, which way are we going to shift? To the left, towards the reactants. Okay, get used to this. Get used to that kind of talk. Q is greater than K, too many products, we're going to shift to the left towards the reactants. That means we're going to make more reactants, so I'll put plus signs here, and lose products, so I'll put minus signs there. Making more reactants. We're going to pick a variable. The variable we're going to use in this book, in this course, is X. Leave a little space between the sign and the letter X. So we're going to form X amount of reactants and lose X amount of products if we shift left. But we have to account for stoichiometry, and the way to account for stoichiometry is you got to put the lowercase letters in here. Okay, that accounts for the stoichiometry. Now, if Q is less than K, we're losing reactants. We're shifting to the right. We're losing reactants. And we're gaining products. Okay, so this is case 2 in the row below. That's all for the C row, the C line. That has to do with change, or Q. Okay, so it depends which way we shift, what happens. Now we're going to go to the final row, and this is called the E line, or the E row. And this has to do with equilibrium. Equilibrium. Or the equilibrium, I'll put below, concentration. Equilibrium, concentration. The equilibrium concentration is simply the I line plus the C line. Initially, plus the change will finally end up at equilibrium. So this is, I'll put it right here, I plus C, right, kind of vertically there. I plus C is going to be this last line. So, for example, for A, it'll be I plus or minus AX. I'm just adding those two lines for both cases. For the B, it'll be J plus or minus BX. Okay, or the sum of those. The equilibrium concentration for C is K minus or plus CX. And for D is L minus or plus DX. This is what we call the equilibrium expression. What we call the equilibrium expression. Why is this helpful? It's helpful if I give you the initial concentrations and you have K, you can calculate mathematically the equilibrium concentrations, which are really important to us. We want to know the concentrations in equilibrium. We're going to use that in this chapter, the next chapter after that. It will not go away. This does not go away. So you need to remember this one. Okay. So let me move this up the page a little bit. We're going to work with this a little more. Okay. Now, Q, if I wanted to mathematically find Q from this table, I use the I line because I want to know initial concentrations. Okay? Here, Q tells us shift, but here it tells us the initial concentration. So, it's the products K, L, and raised to their power, C and D, over the reactants, I and J, raised to their power, A and B. So that would be Q if I wanted to find it mathematically. Okay, how would I find K if I wanted it from this table? And don't worry, we're going to do an actual example in a little bit, so you get to see actual numbers. K from this table would be products K minus or plus CX raised to the C, L minus or plus DX raised to the D over reactants. So this is from the E line. I know it's kind of crazy to see it the first time. You'll get used to this as you do lots of problems, and it'll become more and more natural. So if I write a little note here, this is from I, that's from the I row or the I line, and the K is from the E line. And hopefully that makes sense because I represents initial, and so Q is from initial concentrations. The E row or the E line represents equilibrium concentrations, and so I'm just taking the equilibrium lines just from right here and putting them in this equilibrium expression. Okay, and I'll show you how to solve a problem in a little bit. There's one more bonus exciting piece of information here. You see how we have the variable x, the unknown x raised to certain powers? Because of that, it will not be unusual to run into the quadratic equation. So you need to pull the cobwebs off of that thing from junior high and remember how to solve a quadratic equation. X equals negative b plus or minus the square root of b squared minus 4ac over 2a. Okay? You remember that, right? Totally clear? Okay. Sometimes we'll have to use a quadratic equation when we solve these kinds of problems. Okay, let me move this. All right, we have a practice problem here. Gotta tackle this. And this will help illustrate what the heck I was talking about just a moment ago. Okay? You'll get used to it. And as you can see, I have tons of equilibrium problems on YouTube that you can check out. 1A, 1B, 2A, 2B, 3A, 3B, tons of them. And a KP one as well. So feel free to check those out and see more examples than this. But what you're going to notice is throughout the course, for the next many chapters, we will be doing this exact type of problem. So probably in lecture, we'll end up doing at least 20 of them. Okay? You'll kind of get used to it. The more you practice, the better, of course. Okay, so when you tackle one of these sort of problems, what I start by doing is write the reaction down. Let's get going on the reaction. Looks like we've got an H2 plus an F2, and they're both gases go to HF, and that's a gas. Let's balance it, 2. Okay, good. All right, so there's the reaction. Notice the question wants calculate the equilibrium concentrations. If you're ever asked for equilibrium concentrations, the ice table is the only way to get there. Okay? So if you're asked for equilibrium concentrations in any way, you got to use the ice table. That's what I'm going to call this table, the ICE table. And we're just going to start by filling this out, okay, and seeing where we go. And I'll have to do a little work on the bottom of the table in order to solve the question. So we'll be doing scratch work at the bottom. First of all, the initial concentrations is what I want. And we'll want units of molarity. So if this is a concentration type problem, always use units of molarity in the ice table. You're going to see that your textbook sometimes uses units of moles. I do not recommend that. It does work, but it can get you into trouble later on in a future chapter. So I always recommend molarity in the ice table if you're talking about concentration. So in this case, 3 moles of each compound in a 1.5 liter flask. So let's do a little scratch work down here. 3 moles for each one by 1.500 liters. Looks like it's going to be 2 molar. Is that okay? So go back down over here. Everything is going to be 2 molar. 2, 2, and 2. In this particular problem, it says they're all 2. All right. Now we've got to go to the C line and figure out the change. But to do that, we have to know which way something will shift, right or left. How do we figure out which way something's going to shift? How do we do that mathematically? We've got to use Q and compare it to K. So I've got to go down here on my scratch paper and say, okay, Q is products HF initial squared over H2 initial times F2 initial. Well, that's 2 squared over 2 times 2. Looks like 1 to me. Okay? Now, let's compare this to K. Which one's larger? Is Q larger, or from the problem is K larger? K is 1.15 times 10 to the 2. K is larger. Which way are we going to shift, right or left? K is smaller. There's not enough products. We have to shift to the right. All right, let's go back to our ice table now with that information. That information told me which way something shifts, and that helps me in the C line of the ice table. So if it shifts to the right, we're going to gain or lose reactants. Lose. So minus x plus how many x? 2. This 2 is from that number 2 right here. So, just to clarify, this 2 right here comes from that 2 right there. These are just minus x because there's 1's here. So it shifts to the right. That's why there's plus on the products and minus on the reactants. Okay, how do we find the E line? You merely add the I and the C line together. Merely add them. So let's do that. This is 2 minus x, this is 2 minus x, and this is 2 plus 2x. See how I simply added them? Okay, now for Q, when I found Q, remember I used the I line numerically. I used the I line. Now for K, I'm going to use the E line because E is equilibrium and K has to do with equilibrium. So now we're going to move to solving for x. Before we do that, just a second. The question said, if you review the question says, calculate all equilibrium concentrations. That means it wants to know all these here. This, that, and that. That's what it's looking for. But the problem is we don't know the value of x. So if we can find the value of x, we can find all these values. Does that kind of make sense? Okay, so that's what we're doing now. Let's go down here. Using the E line, I'm going to find K. K, just write out the formula, HF at equilibrium squared over H2 at equilibrium times F2 at equilibrium. Products over reactants. Or 2 plus 2x squared over 2 minus x times 2 minus x. And remember, all that came from the E line up here. So I'm getting all those from up here. Okay. K has to do with equilibrium. So I just plugged it in for each one. All right, let's go to the next page. We now have to simplify and solve for x. Let's fill in K. K is given. K was 1.15 times 10 to the 2. That equals, Okay, help me out here. This is 4 plus 4x plus, 8x. 8x plus what? 4x squared. Craziness. What's this one? 4 minus how much? 4x plus x squared. You got to solve this craziness. How are you going to solve this? You can't, somebody said graphing, you can't graph on the test. Yeah. So if you can't do that, what do you have to do? You could, yeah. One option is, and you're told that's totally fine, you could take the square root of both sides. 2 plus 2x over 2 minus x. That's another way to solve it. So you could say, square root of 1.15 times 10 to the 2. That's 2 plus 2x over 2 minus x. So you really have two options. This one probably would not use the quadratic. This one would definitely use the quadratic formula. Got to go through one of those methods. Because there will be certain times that you have to use a quadratic, I just want to mention something about it. So you've got to go home and figure out how to do that, okay? You got to go home and figure out, how do I use a quadratic formula? You need to solve for x. Here's sometimes what happens. So x is going to be 1.528 is what I got. That's what I got. Sometimes, and you'll see, I'll do another example at the next class about this. Sometimes you get for a quadratic, how many answers do you get? 2. But you can't possibly have 2 concentrations existing at the same time. So what happens is the math gives you something that is not true chemically. In that case, the second answer will be unusual. Meaning, say you could get like a negative number for x. Well, that's not possible to give a negative concentration. So if one of the answers will always give you a concentration that is not possible, that is a negative concentration. So you want to take the one answer that's going to give you the positive concentration. It's this one in this case. Once you find x, then you're pretty set, because H2, in this case, from the ice table equals F2, which is 2 minus x, and HF is 2 plus 2x. So this is going to be 2 minus 1.528, or 0.472. And this is going to be 2 plus 2 times 1.528, or 5.056. Okay? You got to take care of this part. One more thing. What's the units? Don't say none. It's molarity. Remember, going backwards, you drop going from molarity to K, you got to drop the molarities because you know there's no units. Going from K to X, you got to add back in the molarity because it would add back in from the activities. All right, let's stop right there. We'll do some more examples next time.